Hello, my name is Bobby Hilster, and I am your particle model guru. And today we're going to be talking about how the particle model comes up with the fact that there are two gravities. In in the future, we'll be covering a lot of different things using the particle model. We'll be covering gravity, light, magnetism, electrostatics, circuits, and even some chemistry. So go the right way. In the particle model, we have three main particles that we use to explain all those things. The particle model suggests that the atom is made from two particles, the nucleon and the G1. The nucleon replaces the neutron and the proton. The G1 particle replaces the electron and the photon and the graviton. Today we will explain why there are two gravities, and we'll be using the G1 particle. So let's start with, we are going to talk about two gravities, let's start with the first one. And we're first going to talk about Newtonian gravity. Now, when Newton invented gravity, he had no direct evidence of gravity. You can't see what's causing the motion. What Newton had was indirect evidence, and that evidence was in the form of motion. Motion means that we're talking about speed changes or direction changes or both. And in particular, he looked at the motion of the apple and the motion of the moon. So let me use my hands to describe a little more detail what Newton did. So here we have the Earth, and what Newton observed was that when you drop the apple, let it go, it falls and it moves towards the center of the Earth. In fact, it moves sideways on this side, over here, bottom, top, front, back. It moves in all directions, always moving towards the center of the Earth. Further, he observed that if you're at sea level, you drop it, or you're just above sea level, drop it, it goes to the center. You get on top of a tall building and drop it, it goes to the center. You go to the top of a mountain, it goes to the center. Hot air balloon or whatever, all the way up, this gravity he invented has a force all the way up there, including, he suggested, that it got all the way up to the moon. And Newton knew that you had to have this force pushing down on the moon and a velocity of the moon combined to make the moon orbit. This is his observation, starting from sea level up, all the way to the moon. And he says, I think that's the same force that's doing all of this, and I'm going to call it gravity. So one of the pictures you tend to see is this picture here, and it shows the direction that the apple is falling towards the Earth. It also can be interpreted as the force of acceleration that moves the apple from wherever it is towards the center. This is a common picture that is seen quite often. And of course, you can have the same gravitational field. Moon has its own gravitational field. I'm not explaining how it got there. Newton didn't explain it either. He just says, I think there's a force that causes this to happen. And in this case, what you have here is the force of acceleration on the moon is towards the center of the Earth. The moon has a velocity and it has a distance between the moon and the Earth. And the interesting point is a formula derived by Huygens says that if this acceleration is equal to the square of the velocity divided by the distance, you'll have a circular orbit. Of course, the moon is not circular, but that would be the condition that you would need. And so that's whether it's the apple here on the surface or whether it's the moon way out here, this force of gravity is towards the center. In the particle model, and I have been working on gravity for at least 10 years, I was using a gravity particle as the element that would push the apple down towards the moon, and I called it a gravity particle. That's the term I used. Okay, switching a little bit. That's Newtonian gravity. Switching a little bit. A couple of years ago, came up with the idea that light is actually a stream of particles. So if you look at this top line, you have a stream of particles moving to the right, and other ones all moving to the right. And they have a particle distribution such that at the peak there are more particles. In the valley there are fewer particles. At the peak there are more particles. This is the particle model for light. It's not a wave. It has a wavelength from peak to peak is the wavelength, but it's not a wave because there's no medium. These are individual particles spaced apart. They may be clumps of particles, but they're moving at speed c to the right with clusters of particles at each peak and very few particles in the valleys, and this pattern repeats. So when we did that, that's David and I worked together on this. When we did that, I decided to apply this to refraction. Now, you remember what I said about Newton. Newton observed the motion of the apple and the moon. I pulled up this figure, and so this shows light, red light, going to the prism, refracting, and going through the prism, refracting again. But now you have to consider, we're using the particle model, that this is a stream of particles with that repetitive pattern. And what happens is the diagram and shows that the direction changes. That's a change, that's motion. A change of direction or a change in velocity is a change in motion. And Newton says when you have a change like that, you have to have a force. And I said, well, now, where would I put the force? Like Newton did with his gravity, where would I put the force to cause that to bend? And I drew this picture. I just guessed. I didn't know initially that that's really what it was, but that's where I put it. And I says, okay, that's cool. That would look, a force in that direction looks like it would cause the light to bend. It's coming in from the left, it's bending to the left. And I said, oh, wait a minute. Down here, there's another bending, another turning. And what kind of a force would that be? So I drew another line. And I said, wait a minute, look at that. That starts to look something like Newtonian gravity, where you have forces pushing on this side, forces pushing on this side. What about over here? And what about over here? What, is this a type of gravity? I asked that question immediately when I drew this bottom picture. So I tried to verify the direction of the force. This is a little setup I did at my own place, bought a kit. There's a prism here and a red light coming in at a 45-degree angle, coming from the left, bending left, and when at the other end coming, it bends right. And that's almost a duplicate of what you saw in the other picture. Well, I tried it on the other side and got basically the same result. Coming in at 45 degrees from the right, it bends right, bends to the right, and up here it bends back to the left. I tried a third time. This time I took two lights and pointed them straight. Okay, if the force is perpendicular to that surface, like I drew in the other picture, then the light doesn't bend because it's only moving it through the prism and doesn't bend left or right. All of that confirmed to me that the forces were, and that's true all the way around the prism. In fact, this is what I ended up drawing. Here's a prism, and these are the forces that would bend the light the way we see it being bent. And the question is, what is this force? So let's compare. On the left, we have the Earth with its force, Newtonian gravity. Is this on the right? Is that Newtonian gravity? That's the question. Okay. So let's look at it more carefully and analyze it more in detail. If you look on the left, these arrows are pointing, are actually perpendicular to the surface of the Earth all the way around, three-dimensionally. These are perpendicular to the surface all around. So that's the same. That's the same. However, on this side, the left side, the Earth, all of these arrows are pointing towards the center of gravity of the Earth. That's not true over on the right-hand side. Almost all of the forces are pointing somewhere else. Maybe there's a force in the middle of each edge that, yes, is going to point to the center of gravity of that prism, but that's the exception, not the rule. These are not pointing the same direction. Another situation, Newton observed the apple. The apple moves, the apple is a rather large object. It has atoms, it has molecules. The moon is a large object. It has atoms and molecules. And so the size of what Newton is moving is very large. But over here we have light, and if light is a particle and light is moving at speed c, we got a whole different particle. So it's not very likely that the force required to move the apple and the moon is the same force as what's required to move and bend light. And of course, the speed is different. The speed of the apple and the moon is very slow. The speed of light is extremely fast. There are enough differences there that there is no way that these forces on the right are Newtonian gravity. But I don't have all the information here, but in later videos, I will show you how, in fact, this force does act very much like Newtonian gravity, but it is different. Okay, so at that point, I started talking about gravity 1 and gravity 2. We got two gravities. Gravity 1 is Newtonian gravity. Gravity 2 is, for the time being, I'll call it refraction gravity. And Dave and I, as time went on, we started to abbreviate that to the G1 and G2. And as I said at the beginning of the presentation, I was going to explain the fact that there is a second gravity based, in this case, on a particle that we now call G2. Okay, so just to summarize and show how the similarities really work here. Gravity 1, which is Newtonian gravity, what it does, this is not how it works, but what it does is it holds air and water attached to the Earth. It holds loose rock, it holds me, it holds you, and it even holds major pieces of the Earth together. The second thing it does is it keeps the moon in orbit. Gravity 1 keeps the moon in orbit. This is the same picture with the moon having this velocity and this acceleration towards the center. The moon will orbit elliptical or spherical depending on the numbers involved. Of course, the gravity goes further than that. It goes the solar system. Our solar system, when the Earth orbits the sun, gravity 1 controls that. When our solar system orbits the galaxy, gravity 1 controls that. So it's not just the Earth, it's not just the Earth and moon, it's at the galactic level. That's how far gravity goes and can control the motion of these larger objects. Now let's take a look at gravity 2. Now, I'm going to say this, but I really haven't explained the details as to why I would come to this conclusion, but I'm going to draw the analogy now, and as we do later videos, you will see why this is true or reasonable. The G2 gravity actually holds the nucleus, multiple nucleons together, just like G1 holds the Earth together. G2 keeps G1, which is the alternate for the electron. Remember at the beginning I said the G1 is a substitute for the electron, the photon, and the graviton. Okay, so in this position, the G1 is acting like an electron, and the nucleon is like neutrons and protons, but the G2 keeps this in orbit in a very direct gravitational sense, like Newton's gravity, like G1 gravity. Further, it'll keep the molecules together. You have multiple atoms making a molecule, water, H2O, it's held together by this G2 particle. Interesting point. We've all heard about nuclear binding forces and how strong that is. This force, as the particle model is proposing, is in fact the nuclear binding force. Over here on the right, it is the atomic binding force. And if you want to extend it further, it's the molecular binding force. It's what holds things together, including my finger. Without the G2, my finger would fall apart into little particles. Okay, so what the particle model is saying is there's two levels of gravity. G1 is Newtonian. It deals with Earth, sun, moon, apples. There's G2 gravity, which deals with light and specifically with refraction, although it does apply to magnetism, electrostatics, circuits, and even chemistry. There is only indirect evidence of G1 and G2. Newton saw indirect evidence, apple and moon. I showed you indirect evidence using refraction that there is possibly a force that looks like gravity, and we're calling that G2 gravity. There's only indirect evidence for levels 1 and 2. Could there be a 3? There is no evidence, direct or indirect, that 3 could exist, although the model might suggest so. And so in conclusion, particle models suggest that there are two gravities, G1 Newtonian gravity, G2 is like right now called refraction gravity and helps with all these other things. Well, you got to give Einstein credit. He said that gravity bends light. We're saying he just picked the wrong gravity. Okay, my name is Bob D. Helster, and I am your particle model guru, and I will be back to explain more of the universe using the particle model. And thank you for your attention.